The story of our nation's air defense has of necessity been a story of rapid changes. Changes in concepts, strategies, and weapon systems brought about by the ever-increasing demands of the time. And though the skies of the future may belong to the age of rockets and missiles, the silhouette of the long-range missile bomber still dominates. The following is a profile of the B-52 and an account of the events of the past year which developed the most powerful bomber ever to patrol the air, the B-52H. Four events of 1960 best illustrate the stages of development and progress of the latest version of the missile bomber. During the latter part of March, the first developmental engineering inspection was held at Boeing's Wichita division to evaluate the innovations to the B-52 which brought about a model change. The new turbofan engines were such a significant change that the engine pod was the subject of a separate DEI a few months earlier. Major interest centered around the airplane mock-up, which displayed such items as the ASG-21 fire control system, the new ECM systems, including a modified shaft dispenser, the numerous changes associated with improved low-level capability, such as the single-motion seat ejection and the bomb navigation system, which incorporates terrain avoidance radar. Air Force acceptance of the planned configuration for the H model during this DEI paved the way for its continued development without delay. The second major phase of development occurred with the delivery of the first 47 body section in August. The H began to take form. With experience accumulated over years of building Stratofortresses, the complexity of this airplane presented few problems. Joining of the wings and major sections was accomplished on schedule. The last assembly stage before moving to the camouflage hangar was the change installation where all current ECPs were installed. The rollout of the first H marked the completion of the assembly stage as it was readied for a key pre-delivery inspection. The fourth and last developmental phase was represented by two significant inspections. The contractor's demonstration inspection, held the latter part of November, followed by the contractor's technical compliance inspection. The ground support equipment required for maintenance and overhauling the new systems was demonstrated at the CDI. The majority of the items displayed and demonstrated were applicable to the new model, but some of the items procured for support of earlier models were also included. Immediately following the CDI was the CTCI, which brought more than 170 Air Force personnel to the Wichita Division for a key pre-delivery inspection of the first H model. This was the first opportunity for the Air Force to conduct a thorough scrutiny of all changes included in the first B-52H airplane. Because of the thoroughness of previous DEIs and close coordination during the design of the changes, no major changes were requested. In addition, only a small number of minor changes were necessary to meet Air Force requirements. Behind the relatively short span of a few days of thorough inspection lay many months of experimentation, exploration, and research. The major components which provided a significantly improved airplane over all previous models of the B-52 represent the latest advancement that technology has developed. A major contribution to the superior performance of the new model is the Pratt & Whitney turbofan engines that enable the missile bomber to fly farther than ever before without refueling because of lower specific fuel consumption. The added thrust of the turbofan engine allows system simplification by elimination of the water injection system. Valuable information concerning performance and all pertinent data on the operation of the engine system was collected on a ground test stand and evaluated before the prototype airplane was flown. The G-test bed airplane with the turbofan engines has flown over 100 hours during 1960, with tests being conducted at altitudes up to 60,000 feet. The flight testing explored critical flight conditions, obtained extensive performance data, checked out engine systems, and provided confidence in the B-52H production design. Performance runs with the turbofan engines have shown average specific range improvements over the B-52G of 19.2% for high-altitude cruise conditions. As a missile platform bomber, the latest model of the B-52 has the capabilities of launching 3 different types of missiles, each designed for a separate purpose. All B-52H airplanes are scheduled to be delivered with complete provisions for carrying and launching 4 GAM-72A Quail decoy missiles. The range of the missile is 340 nautical miles at high altitude. Its mission to confuse, dilute, saturate, or otherwise degrade the enemy's radar and IR-controlled air defense systems. This both improves the destructive potential and reduces the cost of strategic bombing missions. Minor modifications to all B-52s previous to the H model were necessary for carrying the Quail. The internal changes were easily made without cost to the plane's performance or its ability to carry other strategic stores. The developmental program of the GAM-77 Hound Dog missile will be completed by mid-1961. The air-to-surface missile has a maximum range of 634 nautical miles and can deliver a nuclear warhead by penetrating at high or low altitude. An advanced version of the Hound Dog, the GAM-77A, is being developed by North American. This missile will have an increased range capability of up to 700 nautical miles and will be equipped with a cartridge starter, making it compatible with the quick alert concept of the B-52H. The third member of the B-52's missile arsenal is the GAM-87A Skybolt ballistic missile, currently under development by Douglas Aircraft Company. The Skybolt Provisions DEI was held at Wichita in June, when the mating of the missile to the B-52G wing was accomplished. The missile DEI was held at Culver City, California in August. The final Provisions DEI to be held at Wichita in January of 1961. GAM-87A provisions will be installed prior to the time the missile and its associated equipment become available. The maximum range capability of the ballistic missile is 1,050 nautical miles, and it can deliver a nuclear warhead on enemy targets from either high or low altitudes. When the Douglas missile reaches operational status, the Stratofortress Skybolt combination will unite the human judgment of a manned bomber with the hypersonic speed of a ballistic weapon, representing the ultimate in weapon system capability. The AN/ASG-21 fire control system is one of the major changes to the airplane configuration, which markedly improves the B-52's defense capability. The major obvious differences between the old and new systems are the tail configuration, dual search track radar, and the new 20mm Gatling gun. Well in advance of actual firing, the entire ASG-21 system underwent a thorough laboratory checkout with the aid of a complete mock-up. The dual search track radar, shown under testing conditions, operates in the KU frequency band, which minimizes interference from lower frequency X-band ECM. Static firing of the Gatling gun was accomplished near the end of the year. Close-up high-speed photography reveals the Gatling gun principle, which discharges at the rate of 4,000 rounds per minute. To date, all ground firing activities have successfully been completed. The Fire Control System Flight Test Program is currently being conducted on a prototype airplane. Approximately 60 hours of flight time with numerous fighter passes have been completed, and the results indicate that the system target detection and acquisition will meet specification requirements. Since early B-47 production, ever-increasing requirements for electrical power have presented a design and supply problem for both the Air Force and Boeing. B-52H design studies pointed up the desirability of providing electrical power supplies which would accommodate revised and improved electronic systems and components. In addition, electrical power supply and drive design changes were necessitated by cowling redevelopment of fan engines on the B-52H. The B-52H is equipped with a 120 kVA electrical power system. Power is furnished by 4 120 kVA brushless generators. The constant speed drive, which will be delivered on early B-52H airplanes, will be rated at 60 kVA, pending completion of qualification tests. Development and testing of the constant speed drive is continuing. When completed, internal changes will be made in the drive, upgrading it to 120 kVA capability. Throughout the year, several structural programs have been conducted designed to assure the structural integrity and extend the life of the B-52. One such program, the B-52G cyclic test, not yet completed, is helping to determine the fatigue-sensitive areas of the airplane structure. This is particularly significant in view of new strategic operational concepts for the B-52, such as low-level penetration. The test also provides information for establishing structural inspections and required modifications to extend the structural life of the airplane. During the past 12 months, the airplane was cyclic tested to a repeated load spectrum representative of over 200 simulated SAC missions. The test revealed some critical areas which have resulted in changes both for B-52H production and modification kits for existing B-52G models. Timely kit installation will improve the structural life of the critical areas as well as prevent premature structural failures on the SAC fleet. Results of the cyclic test have proved invaluable, both from the standpoint of locating critical fatigue areas and for calculating structural airplane life under varied planned usage. Major design changes in the airplane meant extensive flight testing for structural integrity, flight load surveys, and flutter. Among major structural integrity flight tests were those which measured airplane capabilities with and without the GAM-77 attached. Flutter tests proved, as predicted by wind tunnel findings, that the airplane was safe from flutter throughout its weight and speed range. Modification of the airplane escape system was evaluated under several flight conditions. Findings indicated that crew members have been given a greater margin of safety than ever before. This is especially true under low-level conditions. Several seat firings were conducted during the year at the Edwards Air Force Base range. An anthropometric dummy, clothed and equipped similar to a regular crew member, was ejected at altitudes of approximately 800 and 14,000 feet. During preliminary testing, changes were made to provide maximum reliability of all ejection seat components. Early in the year, an altitude record for the B-52 was set when the H prototype airplane, powered by the turbofan engines, exceeded 60,000 feet at a gross weight of 188,000 pounds. Though known for its superior performance at altitudes above 50,000 feet, the B-52 also underwent extensive testing to investigate its low-level capabilities. To meet a demonstration requirement, both a G and a D model of the missile bomber successfully flew a VFR low-level mission profile on 2 separate occasions. The course, originating from Wink, Texas, extended through 6 states, over 1,019 miles, ending in Chadron, Nebraska. The mission profiles were flown at an average altitude of 500 feet and at speeds which averaged over 400 knots for the entire flight. Further flight testing of the terrain avoidance radar was accomplished throughout the year. During this program, low-level flying has been demonstrated under instrument flight conditions, solely with reference to the terrain avoidance radar and normal flight instruments. One flight was made under these conditions for a distance of 1,000 nautical miles at an average altitude above the terrain of 750 feet and at an average airspeed of 300 knots. Tied directly to low-altitude flight tests is the operation of a Boeing-designed and built low-level flight simulator. The simulator has provided invaluable data, particularly in connection with the implementation of the terrain avoidance radar used in low-level flights. Simulated flights have enabled human factors engineers to evaluate suitability of instrumentation arrangement and determine how well the pilot performs with terrain avoidance radar while flying under simulated low-altitude conditions. Continued peak performance of the B-52 would not be possible were it not for the success of its major support groups and activities. With the addition of 2 on-site locations, one at Biggs Air Force Base, the other at Barksdale Air Force Base, modification and maintenance activity was expanded to 11 sky-speed bases. Provisions for both the GAM-72 and the GAM-77 were installed at depot level and sky-speed bases in a 2-pronged effort to improve the missile-carrying potential of the SAC fleet as quickly as possible. The sky-speed program has continued to prove its merit as the best means of swiftly updating all models of the B-52 as each new improvement is developed. In addition to the sustained sky-speed efforts to update the fleet, Project Turnkey was initiated at Wichita to handle the largest major revision of any B-52 model. The in-plant modification program accompanies a similar effort being conducted at both Sama and Okama. 66 E-model airplanes will be modified at Wichita to increase their capacity for low-level penetration and carrying of the GAM-72 and GAM-77 missiles. As in all airplane model changes, numerous items of ground support equipment are required for maintenance and modification activity. For example, this QEC test stand was developed for testing of replacement turbofan engines. The new stand permits thorough testing and calibration of an engine, complete with accessories, before it is installed on the airplane. Previous test stands did not allow testing of engines in a complete QEC configuration. The QEC test stand would allow SAC crews to have a supply of fully tested engines on hand at all times and eliminates using airplanes for engine test beds. Should trouble develop in an engine, it could be replaced with an engine already checked out for flight. Manufacturing continued its progress in the vital area of research and development of new processes. Among the most significant was the development of the shear, or the flow turning process. It further extends manufacturing capabilities for the forming of one-piece unwelded parts, difficult shapes, such as cones, tubes, and spheres. The use of this process provides consistent production of close-tolerance parts at reduced part cost. The die forming of radomes was another process developed to solve a specific manufacturing problem. The problem in this case was to find a mechanical method of producing void-free, high-temperature radomes. The absence of voids in radomes not only helps deter delamination of the layers, but also means that the part's electrical properties are improved. Die forming of this part has meant an extension of previous design limitations, enabling the production of previously difficult shapes with a significant reduction of man-hours. Before the development of the process which produced this spiral antenna, existent manufacturing techniques were unable to approach the theoretical electrical properties of such a design. Tape-controlled milling produced the part from a theoretical equation, thereby eliminating the need for dimensioning. Another support activity of the new H model included the Air Force Factory Special Training Program. Over 425 Air Force personnel this year have undergone extensive electronics and mechanical systems maintenance training at the Wichita Division. In addition to the normal in-plant training of company personnel, instructors were called upon for the first time to conduct and supervise training in the field. Training sessions to handle the rework of the B-52 fuel quantity system and installation of wing kits were conducted on-site at all sky-speed bases by Wichita instructors whose specialized knowledge made immediate training available. The history of events and activities of the B-52 in the year 1960 gives strong evidence that the manned, long-range missile bomber, more than ever before, has a vital role in the Air Force concept of military strategy. It is a proved operational weapon capable of weathering an attack and retaliating selectively and decisively against any enemy.
Washing a B-52 is no ordinary job. There are 17,436 square feet to cover on the outside alone, and that's equivalent to approximately 64 automobiles. Within just a few hours after the airplane reached the modification position, where it would remain for the entire period of rework, the area had become a beehive of activity. One crew removed the 8 jet engines. Another began dismantling control surfaces. The landing gears were removed. The B-52 was beginning to lose its identity, but there was a sound purpose behind it all. This was the first time this new bomber was to undergo such extensive and thorough maintenance. The first opportunity to get beneath the surface and find out how it was holding up after 686 hours of the most strenuous flying possible. Before this airplane is ready for redelivery, 119 changes will have been accomplished and 509 technical orders complied with, requiring approximately 3,500 separate jobs. Probably the most extensive single modification to be incorporated is the major change in the B-52 wing trailing edge structure. This change replaces the conventional structure with bonded panels and honeycomb construction to eliminate deterioration of the trailing edge as a result of sonic vibrations produced during full power engine runup, a condition which becomes extremely critical when water injection is employed. The first major engineering responsibility for the B-52 bomber came to Boeing Wichita in 1956 with the assignment for design and development of a new wing as part of the B-52 Model Improvement Program. Constructed of extruded panels embodying an integrated stiffener, this new configuration will become a self-contained fuel tank, or in the vernacular, a wet wing, eliminating the self-sealing cells presently used. Panels measuring some 80 feet in length are the largest single extrusion ever produced. Mock-ups such as this, representing a section of the new wing, were used extensively for engineering evaluation and testing to determine the feasibility of the new design. In simple terms, the new wing will provide a greater area for fuel storage and at the same time effect a notable weight reduction. Both factors will result in increased range and performance for the B-52. The installation in 1956 of this 100,000-pound Boeing-developed fatigue testing machine marked another step toward increasing versatility in the Wichita engineering test facilities. Greater versatility also was achieved in electronic computing. A year ago, the Boeing analog computer, an electronic flight simulator, looked like this. Today, after extensive rework and modernization by Boeing Wichita Engineering, a vastly improved system is available for electronically solving many complex flight problems on both B-52 and B-47 airplanes. The new design incorporates an automatic potentiometer readout system and a unique hold condition which permits the freezing of a problem in the computer for any desired length of time. A centralized computer console from which all problems can be controlled and monitored. And a complete patchboard system which allows problems to be patched up in 30 to 45 minutes compared to weeks and months required on the old computer. All these features add up to one thing: greatly increased utility and 8 times greater computer accuracy. Amid all this activity, coincident with the beginning of a new production era, an equally colorful era was coming to an end. On August 20th, 1956, the last B-47 was rolled from final assembly at the Wichita plant. This, the 1,390th of these medium bombers, symbolized a production program so efficient and so well organized and integrated that a record of 59 consecutive months of B-47 on-schedule delivery was established. When the Air Force took delivery of the unit number 1,390, the Wichita B-47 production program was officially at an end. By no means, however, did the B-47 disappear from the flight lines or the factory. Since 1952, Boeing Wichita had been entrusted with full design responsibility for the B-47. And from an engineering standpoint, there was still much that could be done to improve and adapt the airplane for a wide variety of strategic uses. At the beginning of 1956, Project Crossbow was approaching the flight test phase after months of design investigation and feasibility studies in the wind tunnel, and flutter testing with both the B-47 model and the actual Crossbow airplane. Before the B-47's missile carrier capability could be conclusively proved, however, many hours of testing in the air would be necessary. To determine the performance characteristics and operating limits of the modified bomber, proof testing throughout speed ranges up to maximum safe operating speed, and at various altitudes and airplane attitudes, had to be accomplished. During these flight tests, longitudinal stability of the airplane during high altitude, high Mach number flight, and during low altitude, gear down flight was evaluated. Data was obtained to determine the drag associated with various crossbow missile configurations. In-flight flutter analyses were conducted to establish airplane missile placard airspeeds. And finally, actual missile drops were made to ensure satisfactory separation and trajectory of the weapons at anticipated speeds and altitude. During all these and many other phases of the crossbow flight test program, the B-47 maintained satisfactory performance, with no indication of adverse effects resulting from the structural changes that had been made, or the added mass being carried. Crossbow was proving beyond any doubt the versatility of the B-47 in adapting to many special purpose configurations. By December 1956, the engineering and modification of two B-47E gravity bombers to a DB-47 Director bomber configuration had been completed. These planes will be used for Air Force evaluation and suitability testing in the capacity of carrier vehicle for the Bell GAM-63 guided missile. Meanwhile, modifications required to convert 30 more B-47s to the DB configuration were being worked along with Project Ebb-Tide, the regular B-47 Modernization and Iran program. Current planning calls for 25 of these bombers to be fitted with the required DB-47 equipment, which is then removed and shipped to an Air Force storage depot for installation at a future date. These airplanes themselves are then delivered to the Air Force in the B-47E or gravity bomber configuration. Actual launchings of the GAM-63 Rascal from a DB-47 configuration airplane were conducted during the year to evaluate the ability of control equipment to guide the missile to its target. Early in 1956, 15 RB-47E airplanes had been modified and delivered to the Air Force as RB-47K models, incorporating special equipment for electronically gathering and recording weather data. These airplanes will be used to collect weather information vital to the successful planning and culmination of hundreds of B-47 and B-52 global training missions, flown daily by the Strategic Air Command. As the B-47 continued to prove its mettle, other modification possibilities were under investigation, with the addition of two ECM pods suspended from the fuselage. The basic B-47 configuration became a prototype external ECM pod aircraft. These external pods will have provisions for carrying ether, ECM, or chaff dispensing equipment. The design, construction, installation, ground, and flight testing of this prototype were accomplished at Boeing Wichita as one of the major B-47 programs in 1956. In the wind tunnel, still another version of the B-47 was being readied for its first flight to provide information required in the development of a prototype high-speed, high-altitude tactical tanker from a B-47E airplane. Basic modifications in this instance will include an additional bomb bay tank for increased fuel loading capacity, and the enlargement of wingtip tanks to accommodate refueling equipment consisting of a 155 horsepower air turbine, the independent hydraulic system which it powers, and which in turn will drive the refueling reel and fuel transfer pump. With an operating range covering a 1,000-mile radius, the tanker version of the B-47, designated the KB-47, will be equipped to formate with 2 fighter aircraft simultaneously and will be capable of offloading a maximum of 50,000 pounds of fuel at the rate of 600 gallons per minute from each wing tank. Other than the KC-135, the KB-47 will be the only other airplane capable of fulfilling refueling requirements of the Tactical Air Command's Century Series fighters. In 1956, Boeing's long-standing policy of encouraging and subsidizing individual inventiveness once again justified itself. Working with a collection of test tubes, speakers, copper tubing, and this specially built vacuum still, 3 chemists from the Engineering Research and Development section were able to solve the problem of radome deterioration due to high temperatures. The solution was in the development of a high-temperature laminating resin, capable of withstanding extreme ram temperature increases due to high speed. This new laminate is not only usable in the fabrication of supersonic aircraft radomes, but ideally suitable for missile warheads and for potting or enclosing critical electronic components in the high-speed aircraft. The year was further notable by the installation and operation of Boeing Wichita's first supersonic wind tunnel. Installed primarily to support research and development on high-speed air inlets for jet engines, this tunnel will become a permanent facility for future model investigation and associated boundary layer research. The tunnel will handle models up to 4 inches in diameter and will attain speeds up to Mach 3 in its present configuration. With slight modifications, this speed can be increased to Mach 4, and a future major revision is being planned to bring air velocity up to Mach 6. In conjunction with tunnel operations, all test runs are covered with high-speed Schlieren movies employing an optical system for photographing normally invisible shock and expansion waves. Movies of this type permit an analysis of airflow patterns around the test model. Late in 1956, Field Service Engineering ordered the first in a series of hundreds of photographs, which will be used as the basis of a complete revision to the B-47E, RB-47E, and RB-47H maintenance handbook. Through stop-action photographs of actual work in progress, the new handbook will greatly simplify maintenance information by pictorially presenting a step-by-step sequence of operations presenting the easiest and best methods of performing all major maintenance on the B-47 model and RB-47 model airplanes. By this simplified approach to maintenance, the Air Force will realize better maintenance in a shorter period of time, with fewer and less qualified personnel. During the 12-month period of 1956, Boeing and Air Force crews logged a total of 3,544 hours alone, performing production and experimental flight tests on the B-52 and B-47 multi-jet bombers. These hours, representing a total of 1,905 flights, were spent in meticulously checking out systems and equipment, analyzing performance, airplane stability, all essential to the ultimate delivery of a high-quality, dependable aircraft of the latest configuration. An additional 506 flights requiring 1,144 hours were flown by support aircraft, such as the Boeing KC-97 Stratotanker, that completed 79 aerial refueling contacts to keep the mighty bombers in the air. Altogether, more than 2 million miles were flown, or a distance equivalent to 85 flights around the world. In review, 1956 at Boeing Wichita has presented a picture of intense activity and indisputable progress. But such activity and progress is by no means unique. 1956 was a typical year, with typical problems and typical solutions, little different from many other years in the long and colorful history of the Boeing Airplane Company. What took place in 1956 is representative of Boeing's constant and relentless drive to keep abreast of the latest advancements in the state of the art. Representative of man's insatiable thirst for knowledge as he directs his tireless efforts to lay bare the scientific fundamentals that permit men to fly higher and faster, and to pinpoint a target miles below and outside the range of his own vision. Representative of the years of constant progress that have culminated in a fighting team second to none, the B-47 medium bomber and the B-52 global bomber, first line of defense in the Strategic Air Command.
Originally put into service in the early 1950s, the B-52 stood as a key deterrent in the Strategic Air Command's arsenal. With its extensive range, the B-52 facilitated the global deployment of the Strategic Air Command's nuclear weapons. In contemporary times, the B-52 takes on roles such as low-level bombing and electronic warfare. While the Boeing B-52 represents the epitome of jet bomber design, its origins can be linked to a decision made by the Department of Defense a decade prior, during a period of national conflict. Throughout a significant portion of World War II, the United States prioritized the development of established technologies. This approach was aimed to facilitate the rapid production of essential wartime tools. Considerable advancements were made in piston engines during this period. The propulsion of every American aircraft engaged in intense aerial conflicts of World War II was driven by piston power plants. Even the formidable Boeing B-29, boasting superior speed, range, and payload compared to other bombers, relied on piston engine technology. While the B-29 was initially perceived as the pinnacle of aviation prowess, its technological supremacy was soon overshadowed by a new generation of aircraft. Early in the war, the United States was taken aback to discover that Germany and Britain had pioneered gas turbine jet engines, propelling fighters at speeds surpassing the legendary Superfortress. In 1944, the American Army Air Force issued a requirement for a jet bomber capable of outpacing jet fighters. Contracts were awarded for at least 5 distinct designs. However, it was the advent of nuclear fission that ultimately brought a swift and dramatic conclusion to the war. While the B-29 was utilized to transport the nuclear weapon, only one aircraft dropped one bomb, leading to the instantaneous disappearance of the city Hiroshima. The devastating capability of a single aircraft raises the possibility that extensive bomber fleets might no longer be necessary to secure victory in modern warfare. The significant human cost paid by America to establish B-29 bases in the Pacific altered the considerations for the next generation of bombers. In the early post-war era, strategic focus shifted towards the capability to deliver atomic bombs over exceptionally long distances, and the Air Force put its emphasis on long-range intercontinental aircraft, a role that Convair B-36 Peacemaker adequately filled for some time. The giant B-36 was really a Second World War design that arrived too late for combat. It required no less than 6 massive piston engines to propel it at what were average speeds. Later on, jet engines were incorporated in pods underneath the wing to augment its propulsion. By 1947, progress was evident in the jet bomber project. During that year, 5 submissions underwent testing, although they were categorized as medium bombers. Among the jets stemming from the 1944 requirement, the B-45 emerged as the first and second most successful. Its straightforward yet efficient four-engine design was officially embraced by the United States Air Force and entered into service in a restricted quantity, primarily fulfilling reconnaissance duties. Consolidated proposed the B-46 as another four-engine jet bomber. With its sleek lines, it stood out as one of the most aesthetically pleasing aircraft of its time, and its performance as an early jet was quite commendable. However, Consolidated's primary focus was on the B-36 production, and the medium bomber project did not receive high priority. Designed by Martin, the B-48 was a cumbersome aircraft with 6 jet engines arranged in mid-wing clusters. One notable feature was its bicycle undercarriage, positioned along the aircraft's centerline and supported by 2 outrigger wheels on each wing. Despite its innovative elements, the B-48 did not capture the interest of the Air Force, and like the B-46, the prototype was ultimately scrapped. In an effort to compete in the jet bomber program, Northrop took its existing piston engine flying wing and outfitted it with 8 turbojets. This wing design demonstrated exceptional efficiency and was notably ahead of its time. However, due to its unconventional nature, it struggled to secure government approval. Nevertheless, Northrop's mastery of flying wing technology eventually paid off 4 decades later with the development of the B-2 stealth bomber. Today, the B-2's wing is a symbol of cutting-edge aviation design, but in 1947, the idea was considered far too revolutionary. Without doubt, the most impressive design offered to the Air Force came from Boeing. The design of the B-47 Stratojet by Boeing benefited significantly from the manufacturer's examination of German data regarding swept-wing technology. To maximize the efficiency offered by these wings, they were crafted to be extremely thin and flexible. Consequently, the 6 engines were suspended on pylons and distributed across each wing. This configuration not only facilitated engine servicing, but also provided aerodynamic advantages for the aircraft during high-speed flight. Due to the thinness of the wings, Boeing opted for the same fuselage-mounted bicycle undercarriage as seen in Martin's B-48. The Air Force adopted the B-47, leading to the production of hundreds during the early 1950s. It proved to be an exceptionally successful design, representing a classic example of having the right design at the opportune moment. Moreover, the B-47 served as an ideal testbed for Boeing to accumulate experience in producing efficient swept-wing jet bombers. One challenge with early jet engines was their relatively prolonged time to reach full power, particularly during takeoff. To counter the issue of prolonged engine power-up, Boeing implemented various iterations of detachable rocket boosters, pioneering what became known as jet-assisted takeoff, or JATO. Following Boeing's renowned piston-engine bombers, the success of the Stratojet project solidified the company's standing with the Air Force for an extended period. The experience gained from the medium bomber project positioned Boeing favorably in the subsequent quest to develop a new long-range heavy bomber, aiming to replace the aging B-36 Peacemaker, an aircraft clearly at the end of its operational life. In a bid to prolong the Peacemaker's relevance, Convair introduced an all-jet swept-wing version designated the XB-60. However, retrofitting an aircraft originally designed during the Second World War failed to impress the Air Force. As early as 1946, Boeing had received a commission to devise a successor for the Peacemaker. The company explored a myriad of concepts, ranging from exceptionally large piston-engine aircraft to those featuring proposed compound supercharged power plants and others incorporating turboprops with jet engines driving propellers. But nothing provided the dramatic increase in performance over the B-36 that the Air Force was looking for. Recognizing the remarkable efficiency of the B-47's fully swept wing, Boeing proposed another all-jet design, loosely based on its medium bomber but significantly larger in scale. This concept evolved into the Model 464-67, and it was eventually embraced by the Air Force as the B-52. An order for 2 prototypes, the X and Y models, was issued in October 1948. However, due to minor issues with the X model, the YB-52 was completed first. The YB-52 underwent testing at Edwards Air Force Base. While its overall shape and fighter-like canopy resembled the B-47, its size and performance far exceeded it. The B-52 featured numerous advancements, including the all-steerable undercarriage that could align forward during landing, when even the aircraft veered to one side, a top-secret feature for several years. Apart from the cockpit layout, changed to a conventional side-by-side airliner arrangement, there were minimal external differences between the prototypes and the B-52s that entered production. Work began in earnest on the B-52A, now named the Stratofortress. Initially, only 3 B-52A models were constructed, but the B model, nearly identical to the B-52A with minor improvements, entered full-scale production. Enhancing the bomber's range was a consistent priority. In-flight refueling, perfected in the late 1940s using Boeing's flying boom method, addressed many challenges. However, during the early stages of the B-52 project, in-flight refueling posed difficulties. The early aerial tankers, powered by piston engines, had a maximum speed only slightly higher than the stalling speed of the jet bombers. In this image, the Y model grapples with the delicate task. The introduction of jet tanker refueling was clearly a safer and more preferable option. The advent of the KC-135 Stratotanker marked a significant turning point, making aerial refueling relatively safe and practical. Another approach to extend range involved incorporating extra-large outboard wing tanks, such as this example capable of holding 3,000 gallons, which could be jettisoned in combat situations. By March 1954, B-52s were rolling off Boeing's production line in Seattle. The planes then went into an induction program, where aircrew and aircraft were blended into one fighting machine. Inside this streamlined form, crews of 6 men mastered the intricacies of the Stratofortress. Compared to the B-36, Boeing's bomber was notably more confined, with every available inch allocated to fuel, payload, and electronics. While the B-36 boasted 6 gun positions, the B-52 had just 1. Instead of relying on multiple gun positions, the B-52 focused on performance and the emerging science of radar jamming for self-defense.
B-52 is a great plane because I liked flying it. It was a fun plane to fly. One of the most challenging things about it was refueling it. You get a plane that big, 500,000 pounds behind a tanker that's 350,000 pounds, and you got to transfer 120,000 pounds of fuel. That's part of the things that make it a great plane. It can go and go and go. I never got to fly it, but they used to fly 24-hour missions in B-52s, just refuel. So I think what makes a great plane where all the crews that flew it over so many years, my father was too old to fly, and I'm one of the younger people flying it myself, but there are probably 25 years older than flying it that are planes 10 years older than them.
The Strategic Air Command demanded the world's premier bomber, setting high standards for both its cutting-edge B-52 aircraft and their crews. Crew members underwent rigorous training, evolving into an elite corps of professionals, a team as adept as the sophisticated aircraft they operated. For over a decade, the Stratofortress and its crew held a singular responsibility, carrying and delivering thermonuclear hydrogen bombs. However, to serve as an effective deterrent, the bomb needed testing to validate its capabilities. Throughout the 1950s, hydrogen bombs were detonated in remote Pacific regions as part of these crucial tests. In the final tests, akin to many conducted earlier, B-52s were utilized to realize the formidable payloads. For the individuals involved, loading the most devastating device at that time conceived by human mind was a matter of precision and routine, a specialized task for the highly trained members of the Strategic Air Command team. Each cargo possessed a 100 megaton yield, a magnitude 100 times greater than the bombs dropped on Japan during World War II. In contrast to the weapons of that era, the device housed in this bomb bay would be decelerated in its descent from the B-52 by a parachute, affording the bomber more time to evacuate the area before the cataclysmic explosion. Driven by the concern of a potential Soviet atomic attack, the United States established an intricate network of detection facilities during the Cold War. Primarily located in the frozen north, the most probable route for a first strike, these early warning systems employed radar watchers constantly monitoring scanners scanning the sky for any blip. The Strategic Air Command maintained fleets of B-52s on operational standby, in a perpetual state of alert, poised to serve as the ultimate deterrent if the need arose. When the red phone rang, the procedure was automatic. Up to 100 Stratofortresses could be dispatched in a few short minutes. The routine was finely honed through regular exercises. The notion of an immediate retaliatory strike by the Strategic Air Command stood as the nation's best defense during the Cold War years. Entrusted solely to carefully screened officers, the task of nuclear deterrence fell upon the shoulders of nuclear-armed B-52 pilots, all holding at least the rank of major. They bore the weighty responsibility of commanding aircraft capable of altering or even terminating life on Earth. However, just as jets replaced piston engines, the B-52 and its high-flying Soviet counterparts were surpassed by a more efficient and lethal technology born in Nazi Germany. By the early 1960s, ground-to-air missiles had reached a level of perfection by both the US and the Soviets, making massive nuclear bombardment by aircraft challenging to achieve. The focus shifted to another delivery method: intercontinental ballistic missiles, or ICBMs. Years of development led to the creation of missiles like Polaris and Minuteman, eliminating the necessity for manned flights over enemy airspace to wage full-scale nuclear war. Despite this shift, SAC's Stratofortresses remained in service, as they still played a significant role in the precarious game of nuclear brinkmanship. The challenge with the ICBMs lay in their irreversible launch, denying politicians the time-honored tactic of saber-rattling and intensifying the risk of international conflict. The B-52, in conjunction with Hound Dog standoff bombs, presented a versatile alternative. Positioned at the very edge of enemy airspace, B-52s signaled America's preparedness to attack while allowing room for last-minute negotiations. The B-52's effectiveness was enhanced by the introduction of the quail decoy, which confounded enemy radar by replacing a Stratofortress's radio signal. Advancements after the Hound Dog led to the creation of the SRAM missile. Compact and deployable in greater numbers, the SRAM could be guided from within the B-52 to targets up to 100 miles away with remarkable precision. In 1965, the B-52 was employed for the first time in Vietnam. While now carrying conventional bombs instead of nuclear warheads, it retained its lethal nature. The wing mounts were equipped with 24 500-pound iron bombs, showcasing the adaptability of the aircraft in various mission profiles. The internal bomb load brought the total payload of each plane up to a total bomb load of 108. Throughout the Stratofortress's engagement in Southeast Asia, B-52s dropped over 3 million tons of bombs. While the use of these high-flying bombers stirred controversy at the time, there's little doubt about the Stratofortress's effectiveness in conventional bombing. Many historians contend that the extensive bombing of North Vietnam during the linebacker operations played a crucial role in compelling the enemy to return to the negotiating table, eventually leading to a ceasefire. In other Vietnam operations, more advanced bombs were employed. Some could be remotely detonated by personnel in other aircraft using infrared viewing equipment, synchronized with enemy activity. Standard 500 and 750-pound iron bombs were the norm for most B-52 raids. To expedite loading and turnaround, the internal bomb load was organized in pre-arranged racks, enabling swift installation. Crews stationed at Guam prepared for the lengthy 8-hour flight to the remote target. The crew in the front office and the solitary rear gunner assumed their positions as each aircraft readied for takeoff.
Well, the primary role of the B-52 in Vietnam was basically tactical bombing of enemy troop concentrations. But it really started out, we used to cut roads early in '67. We did a lot of missions. We were interdicting trucks and supplies, but primarily we were cutting roads to back them up so the tactical forces could make the strikes. Later around Khe Sanh, we were really breaking up enemy troop formations. And we got very, very successful as they had to concentrate their forces. We became more successful at what the role of the B-52 could really bring to bear, which is massive air power.
Our defense posture provides the umbrella under which all competition flourishes in this capitalistic society. So the B-52, because of its tremendous design, lasted a great long time. And because of the philosophy and sometimes the tendency to forget history, which we seem to do in this country, it's lasted a long time as well. It's had to.
During the protracted years of the Vietnam War, nose art adorned more than a few B-52s, reflecting the personalization and character that the crews added to the aircraft. Although nose arts were milder compared to its Second World War counterpart, the missions undertaken were no less perilous. B-52 crews faced the challenges of swift and nimble enemy MiGs, anti-aircraft guns, and, most menacing of all, deadly surface-to-air missiles. Despite these hazards, they pressed on with their mission, embodying the resilience of soldiers who carry out their duties irrespective of opposition. Post-raid, ground crews hastily repaired the bullet-riddled airframes of returning Stratofortresses, preparing them for the next mission. Sometimes, the hits were uncomfortably close. Despite the low fuel takeoff policy, the substantial weight of the bomb load placed considerable stress on the engines, necessitating regular maintenance and often replacements. To ward off MiGs, rear gunners played a crucial role, occasionally shooting down the agile adversaries. These gunners operated from their solitary outposts, utilizing a radar-aimed, remote-controlled array of 4 cannons with devastating firepower. The tail gunner's position was omitted with the introduction of the B-52G and H models. All B-52G and H models were equipped with EVS, electronic visual systems, representing a technological advancement enhancing their capabilities. This enables the pilot and other crew members to see what is ahead of the aircraft, even in darkness and fog, via infrared television cameras and a monitor. This development came just in time as the role of the B-52 had changed from that of a low-level tactical bomber. Today's Stratofortresses may find themselves flying through atomic clouds, with the B-52 shielded by radiation-proof curtains and the electronic visual systems becoming the crew's sole visual connection to the outside world. Despite the evolving mission, red phones and flashing lights remain the standard currency of the Strategic Air Command. When the bell rings, whether in exercises or during wartime, SAC's formidable deterrent force leaps into action. The first order of business for the operations general is to abandon the ground base for the safety and mobility of an aerial combat post. Simultaneously, as the alert is issued, aircrews swiftly converge on their aircraft, perpetually on standby for immediate action. The general takes to the air, with the B-52s following closely. It is only in the safety of the skies that SAC's deterrent force can endure an attack while simultaneously being en route to deliver a response. A high-speed takeoff is deemed essential for survival. In these exercises, preparations are made for the possibility of a nuclear flash, and radiation-resistant curtains are deployed. At this stage, the crew becomes entirely dependent on the EVS and other electronic aids, as looking outside the cockpit becomes too hazardous in the face of potential radiation exposure. Flying low over the ground, each pilot awaits his orders. During this exercise, the B-52s are recalled, yet everyone involved acknowledges their capability to enter enemy territory if the need arises. The exercise concludes, leaving the general satisfied. After nearly 40 years of dedicated service, the B-52 continues to fulfill its mission effectively. But it is evident that the aircraft is approaching the conclusion of its service life.
We went over their arc light, which was 6 months at a time, and I did it 5 or 6 times, I don't remember. But the thing was, is you live with these people, you live with them, you sleep with them, you eat with them. They become brothers, so you trust them with your lives. You literally did, because If an EWO said brake right or brake left, you didn't ask why, you just did it. That means turn the plane left or right because there was a threat coming. You just did it. You knew that whatever he was telling you, he was in the plane with you. And vice versa. You never second guessed the other guy because they were the expert in their position. And that's what the teamwork was. You learned to respect the other guy's position and how well they served the position. The B-52 is getting old. It does need a follow-on bomber, and I think the B-1 is probably that type of an aircraft. Next question evolves is, do we need the B-2s? I don't know. It's awful expensive aircraft.
Almost immediately after the initial B-52 rolled off the assembly line, the Strategic Air Command began the quest for a suitable replacement. The ill-fated XB-70 was an initial attempt, featuring an advanced design that became outdated due to the advancements in ground-to-air missile technology. More recently, there was a swing-wing B-1 bomber developed by Rockwell International. The B-1 offered a blend of high speed and altitude with its wings swept back, as well as more cost-effective low-level flying with the wings forward. The cost of deploying a large number of B-1s was deemed unacceptable to Cater administration, leading to the shelving of the project throughout the 1970s. However, in the 1980s, a revamped version, the B-1B, entered production. This time not in the high-altitude role, but as a low-level bomber. Approximately 100 B-1Bs were deployed by the Strategic Air Command. Although the plane comes with a hefty price tag, if the B-1B proves to match the overall performance and value for money that its predecessor, the B-52, clearly demonstrated, it would be considered money well spent. After about 7 decades of service, spanning a period of remarkable technological advancements, the B-52 still stands as a weapon of formidable power and effectiveness. It remains a challenging act to follow in terms of its enduring impact and capabilities.
This is the consolidated B-36 intercontinental bomber, sometimes referred to as the Peacemaker or the Big Stick. It was the largest conventional warplane ever built. It had tremendous range and a great payload. With its 6 piston engines turning, and later 4 more jets burning, the B-36 for many years projected America's military might.
It was a monstrous airplane. It had 6 engines, and they were pusher props. Now later on they hung jet pods on the ends of the wing, but the early models were all piston engines, pushers. It was a huge airplane, and it was designed then to carry atomic weapons.
But by the mid-50s, its sheer size, cruciform shape, and middling performance worked against it in a world of pure jets. However, in its heyday, the 36 was the very pinnacle of successful giantism. Rather surprising given that a decade and a half earlier, the United States had all but abandoned the idea of operating massive aircraft known as XBLRs, or the Experimental Bomber Long Range. The first attempt, the XBLR-1, resulted in the Boeing XB-15. This was an ambitious and useful experiment that demonstrated the importance of 4-engined bombers. The XB-15 carried a crew of 10. However, its 150-foot wingspan proved too large for practical use. But Boeing's next offering, the XB-17, which followed a year later, perfectly met the needs of the Army. Despite the Army Air Force's decision not to proceed with the XB-15, the political mood in 1938 was undergoing a sea change. With the acquisition of total power by the Nazi Party, American military planners had to contemplate a scenario of German domination of Europe, including Britain. In America in 1938, the question being secretly asked was, what if Britain did fall? Perhaps the only way of striking back at the Axis powers in Europe was with the once dismissed experimental bomber long range. The XB-LR2 came together as the XB-19, somewhat bigger than the XB-15, and in fact bigger than any other aircraft in the world at that time. It was to be built by Douglas Aircraft in California. However, by the time the B-19 first flew, the Battle of Britain had already been won, when a few hundred pilots of RAF Fighter Command were just able to halt the Nazi juggernaut. Notwithstanding these events, the B-19 project continued. Some indication of the project's size can be gained from the scope of its planning. The XB-19 required no less than 4 acres of drawings, 500 engineers, and more than 2 million hours of R&D and construction. The wings on their own had a 212-foot span and were over 1/10 of an acre in actual size. The wings also held 4 giant engines. Each one had more than twice the power of those on the B-15 predecessor. The B-19 even had its own hoists for changing the 16-foot propellers and was able to lift its own massive engines on and off the wings. Each wing contained a lighted passageway enabling crew to reach the engines in flight. The 2 massive main towers were 8 foot high, and each was of 24 ply, using 150 miles of rayon cord and 3 miles of steel wire. All of the flying control surfaces were so large that they could only be operated via power-assisted devices. The rudder alone took up an area of 237 square feet of movable surface. To communicate within such a large aircraft, it was necessary to install a 24-set telephone system and a loudspeaker cum fire alarm warning device. And to enable missions of up to 3 days and accommodate at least 13 crew, it was necessary to have a galley, a wardroom, as well as a bunk room. Such were the proportions of what Douglas liked to refer to as their hemispheric defender. In theory, this behemoth flying machine could fly more than 1/3 of the distance around the world without refueling, perhaps reaching parts of Europe and the return trip too. On June 27, 1941, the B-19 made its first flight from Douglas Aircraft in Santa Monica to March Air Force Base. Despite various suggestions to the local press at the time, the B-19 was really a proof-of-concept aircraft to explore what could be learnt about building giant aircraft. The B-19 also presented the same problems and lengthy delays as Boeing had endured with its 4-year development of the B-15. Knowing that many of the lessons recently learnt were already becoming obsolete, Douglas suggested that the B-19 be abandoned. However, the Army remained firm that the XB-LR2 would be delivered. In fact, the Douglas Company's view may have been quite sound, as the war had necessitated that the 2 prototype long-range bombers be ordered 6 months before the B-19 ever flew. The Northrop B-35 and its competitor, the enormous consolidated B-36, would use whatever data could be migrated from Douglas. In fact, the B-35's design was a totally different concept, relying upon advanced flying wing aerodynamics to gain maximum range, an idea that was far ahead of its time. Nevertheless, it was the consolidated XB-36 which the Air Force adopted. It was a symbol of pure 1940s giantism, and likely would have benefited from some of the ideas incorporated in the B-19. However, it was a virtual flying gas tank, carrying with it all the fuel it needed for a there-and-back European mission. The Second World War had come and gone before Consolidated's giant reached production, and as Britain did not fall to Germany, the 36's absence had no impact on the conflict, although its presence became critical in the Cold War that followed. It was during this potentially cataclysmic test that America's Peacemaker really came of age. The newly formed Strategic Air Command under General Curtis LeMay would regularly fly to far distant territories just to demonstrate its enormous reach. It was all a very effective show of force, although by the mid-50s, one that was starting to be questioned.
The airplane flew like a glider. It was easy to fly. Anybody could have flown it with 5 hours of stick time. It was a beautiful airplane. It's good that they never had to fly military missions, even with the 4 jet engines which were placed on later.
The success of an earlier Strategic Air Command gamble with the B-47 Stratojet medium bomber demonstrated the need for a faster swept-wing, all-jet-power heavy bomber. Yet Consolidated felt they could still provide a ready answer. The B-60 arrived after a standard 36 fuselage was married to swept wings and tail surfaces. It was propelled by 8 turbojet engines. The concept would have been economical, but advances in in-flight refueling made it no longer necessary for massive fuel loads to be carried. The age of giantism was coming to an end. Strategic Air Command wanted a smaller, faster and more sophisticated heavy bomber, and Boeing's B-52 Stratofortress fitted the bill. And in terms of years of service for dollars spent, the B-52 was able to adapt and evolve in a way Convair's Big Stick never could. Still, credit where it's due. The B-36 was for a number of years America's sole intercontinental bomber and served as an effective deterrent, appropriately earning the type its other nickname, the Peacemaker.